Chloe, oh my God, is it bad? Does it hurt? I'm so sorry. Selfie elbow. You never think it's going to happen to anyone you know.
What?
She took so many selfies, she got selfie. Okay, I bring this cartoon up because your generation is weird. If you would look through my photo album when I was your age, we had pictures of friends. We had pictures of places we had been to. If I look through your photo albums, all I see is pictures of yourself. You're a generation of narcissists. The only picture I can take, look, it's me, it's me, it's me. You're weird.
Not pretty.
You are pretty. Anyway, okay, here are our 3 vocabulary words for the day. You get to write them down, and we will fill them in. Yeah. Equilibrium means balance. You need some balance in your photos. See, I show up in
Like 0 photos?
5 of those pictures.
She got it so quick. I take pictures of my friends.
I had a friend once.
I'll take pictures. Same one.
What? Are you saying about you still have to be in the first name?
Peppa.
What?
Stefan being the first name.
We don't know yet. We're just writing them down. Okay, today's lesson is both simple and short. This reminds me of a couple of you.
Oh.
No, I'm just kidding. You guys are short, but you had something. You guys are all geniuses. Equilibrium means balance, so our forces are all in balance. So if they're in balance, they're going to add up to?
Oh, no.
No, we didn't come. So if they're in balance, that means the net force is 0. If I'm in equilibrium, I can only travel at a constant speed in a or not move. Most of the time when we're in equilibrium, we're not moving, but if we are in equilibrium, we could also move at a constant speed in a straight line. An equilibrant, of course, would be a force that we added to the other ones to bring them into equilibrium. You can kind of imply that just from the name. Equilibrant brings it into equilibrium. And statics is the study of forces in equilibrium. So today we will learn how to figure out what an equilibrant is and how to do a static type problem. It's great fun. Yay. And it's easy. If I'm pulling 106 newtons east and you want to balance me out, how hard and in what direction do you want to push? Exactly. You want to pull exactly the same hard as I'm pulling. So we want to be equal in magnitude, but we want to be opposite in direction. Oh yeah. What happens if I'm pulling at 53 degrees, pulling at 129 newtons? And you want to balance me out now? How hard do you want to pull? 129. What direction do you want to pull? The opposite. I want to pull that way. And I still want it to be 129 newtons. But what number goes here? Well, when it was just east and west, it was really easy. I throw numbers in there and suddenly you're freaking. I don't know, man. It's really easy. How much bigger did this get? That's 180 degrees bigger. 180 degrees is always the exact opposite other way. East is 90, west is 270. If I take 270 minus 90, guess what I get? Hey, what do you know? I get 180 because exact opposite is always, you can say it, 180. Okay, so if this is 53 and I want to point it the opposite way, I need to take 53 plus 180. Is that magic?
Yes. Time out. No, it's just where did you get the 53 from?
Where'd I get what?
53. Oh,
Because I said this was pulling at 53.
Yeah.
Yeah. So basically, to make it opposite in direction, I want to basically either add or subtract 180 degrees to the direction that's already there. How do I know whether I want to add or subtract?
If it's getting bigger,
If I'm smaller than 180, I want to add 180. If I'm already bigger than 180, I want to subtract 180. Otherwise, I end up with weird numbers I don't know how to deal with. So that's the tricky part. Okay, so that wasn't so tricky, right? Reviewing yesterday. If somebody was pulling me east with 109 newtons, and somebody else is pulling me south at the same time with 126 newtons, and I want to know what third, fourth, balances these two. Well, clearly we would need a force pulling what direction? If this is going east and this is going south, if I said what two forces, you would want one going north, that was 126, and you'd want one west going 109, but we're not going to have that. We're just going to add one force to balance out these two. So clearly it needs to be something that's going northwest. Is it going to be more north or more west? Well, which one does it have to fight harder? It has to fight south harder than it has to fight east, so it's going to have to go a little bit more north than it's going west, right?
Yes.
Is this making any sense at all?
Yes.
Okay, now, what we want to do is we want to pretend that this red one's not there, and we're just going to say, hey, I can't add these two up very well right now because they are tail to tail, and I want them head to tail. So that means I either need to move the east down to the bottom or the south over to the side. Does it matter which one I do? Let's move the south over. So we're going to take the south and we're going to move it over to here. It's still 126. It's still pointing that way. But now my R starts at my start and it stops at my stop and it goes this way. So to find my resultants, again, I'm going to have a magnitude and I'm going to have a direction. How do I find my magnitude? I Pythagoras. Plus 126. I think he overdid his little square thing there. And if we do that correctly, I got 167 after rounding. Is that what you got?
Yeah.
Did you get that? And then I want to find an angle, and again, my starting angle was this angle, so I want to always do tangent to the -1, and what goes on top? Tangent is what over what?
Opposite over adjacent.
Okay, so the opposite over the adjacent means I'm going to have the 126 over the 109. So second tangent 126 over 109. And that gives me 49 degrees. But I don't write 49 degrees over here. That tells me I have 49 degrees here, which means that my dashed line is 49 away from the green line, which is pointing east. How many degrees is east? Okay, so if this is 90, is this 49 degrees bigger or smaller?
Bigger.
It's bigger. So 90 plus 49 is?
I mean,
139. See, that was yesterday's lesson, right? So now if I want to balance those two out, I want to pull just as hard but in the opposite direction. So if I want to change my resultant into an equilibrant, I want to pull just as hard as he does. So I want to be equal in magnitude, but I want to pull the opposite direction. Again, how do I get opposite? How many degrees bigger? 180. So do I add or subtract here? Well, yeah, see, I'm less than 180, so I'm going to add. If I was over here, I would subtract and go the other way. But here I'm going to add 180. So that would still be a 9. 3 and 8 makes 11. Carrying the 1 makes... So today's section is a whole lot easier than yesterday's was, but it builds right into it, right? So if we understood what we were doing yesterday, then today looks super duper simple. And if we weren't quite all there, then we'll get to practice some more today on doing some of that and make it easier. So the last thing we need to study today is statics. And again, statics was a study of forces in equilibrium, things that are not moving. Right now you're in a static situation. If you're sitting on your stool, your weight is pushing down, the stool is pushing up. How hard is the stool pushing up? Just as hard as you're pushing down. So you're in equilibrium. That's why you're not accelerating upward or downward. You're just sitting there. If I would come over and remove your stool, you would no longer have a force pushing up, and you would suddenly accelerate down. Right? Okay. I'm glad you guys are awake today. Here we have a sign. We are going to open our new restaurant. We're going to serve food. So that's what we're going to call it. So I want to hang this sign up by my building. This sign happens to be 985 newtons of force. That is how heavy my sign is. I want to know how strong does the bolt need to be to tie this cable into the building. To do this, we need to study our statics. So ideally, we want my sign to be moving or not moving? Not moving. So I want all these forces to be balanced out. Now, to judge what all our forces are, what we do is we draw a thing called a free body diagram. We did this on the test before, we just didn't call it this. But on the free body diagram we had on the test, remember we had a little block that was being pulled across the table over a pulley, and there was a weight, and you had to say, hey, my applied force was going this way, and my friction force was going that way, and they were fighting each other. Do you remember that? That was a free body diagram. Some of you didn't do so well on that. You thought friction was helping it or something, and a lot of you pointed, oh yeah, friction goes this way too. No, it does. Okay. But that was last week. This week we're going to look at this. This represents our sign, and we're going to say what forces are actually pulling on this sign. Gravity turns the sign's mass into a weight. And what direction does weight pull?
Down.
The only way weight can pull is that way. So we're going to have W going that way. Is there anything else pushing or pulling on our side? Nothing else is pushing or pulling on the side?
little
That's the
runner.
cable.
See, that's holding it up.
Okay, the cable is pulling. What direction is the cable pulling on the sign? That way. So we'd say, hey, the cable is pulling that way, and we'll call it cable. Is there anything else pushing or pulling on this sign? Gravity turns the sign into weight. We've already talked about weight. You can say it 9 times, it's still going to be weight. Gravity. No, it's still weight. The little block. What's that little block doing? What direction is it shoving it? It's shoving it that. We know this has to shove it this way because if I took this thing out, the sign would go against the building, right? So the only way it's out there is I'm shoving it out. So this little post here, this post is shoving it that way, and that keeps the sign sticking out farther so people can see it and say, oh, I want to go eat there. And of course, it'll go out of business after a month because it doesn't serve Mexican food. Hey, if you serve tacos, you can open up a store in a gas station. But if you serve anything else. Okay, anyway, I love Mexican food, don't get me wrong. But, you know, once a year, maybe it'd be nice to eat somewhere else. These are the 3 forces that are in equilibrium. They're in static situations, so they're in equilibrium. That means they're going to all add up to 0. Now, let's pretend I'm going to take a trip. I'm going to start right here, and I'm going to take a trip that has 3 legs to the trip, and I want 0 displacement. Where am I going to end up? Right where I started. Which means I'm going to have to form a triangle. Same situation happens here. Since I have this force and this force and this force, and they're all going to add up to 0, that means I should be able to head to tail them and form a triangle out of them. So a static situation with 3 forces will always form a. So if I look at my drawing, do I already see a triangle kind of there? Yes, you should. And so then you just say to yourself, hey, if I had a little imagination, I could draw this thing out. Okay, we'll pretend that's a straight line. And we can draw this thing out a little bit longer, and we could say, hey, that kind of looks like a triangle. Do I have any important information here? Yeah, I know that angle, so that's why I drew the triangle around my angle, because I kept that important information. And then do I actually know any numbers? Hey, that was my 985, which is my what? Weight, and weight only acts what direction? So where on the triangle would that go nicely? Hey, on the part that is going down, right? And then the post is shoving over, and then the cable is pulling this way. So the 3 of them just keep head to tailing each other, and I come back to my starting point. So what was I looking for here? How strong is this bolt which is pulling on the cable? So really I'm looking for how big is the cable? That's going to be the hypotenuse. And compared to this, the 985 is the adjacent side. So now all of a sudden I have a triangle that has adjacent and hypotenuse in it. And so I have to start saying, hey, yeah, if I have adjacent and I have hypotenuse, that sure sounds like cosine. So now I say, okay, cosine of what angle? Equals the adjacent side, and my adjacent side is 985 over the hypotenuse, which is my unknown. So again, if my unknown is at the bottom, these are going to trade places, and I'm going to end up with x equals 985 over cosine 55. And of course, my calculator better be in degrees if I'm hitting sine, cosine, or tangent. You go, what? Yes. Did you get 1,720 after rounding? If so, then you're doing something right. So now some of you, when you were looking and I said, how strong does this bolt have to be? You probably said, well, this is under 1,000 newtons, so 1,000 newtons should be overkill on this thing. Because it's certainly not going to hold the whole weight anyway. And then what would happen? That bolt would rip right out, the sign would fall, and somebody would sue you, and we would never find out how good your food was. That would be very sad. Any questions on how to do statics? Guess what you're going to do for homework?
Statics.
Statics and finding equilibrium and stuff, and that's going to be problem B, which is a whole 5 problems.
Too much.
Too much.